Next, we're looking at alpha lactose. So alpha lactose is from D-galactose on the left and D-glucose on the right. And let's identify these galactose and glucose as alpha versus beta. So to do that, we're going to be looking at the anomeric carbon, the very left-hand point. And where is that OH group? This one is up high in the sky, so that's beta. And for glucose, here's the anomeric carbon, carbon number 1, the very, did I say left hand for galactose? Very right-hand carbon. And on glucose, the OH group is down with the fish, so that's alpha D glucose. And when these two come together, they are going to form a connection between in this spot right here, in between these two carbon atoms. So you can see over on the right-hand side, these molecules are set up, ready for us to draw in the connection. Now, when the galactose and glucose, when any monosaccharide and monosaccharide are coming together to make a disaccharide, the interaction is always happening between the two OH groups in the monosaccharides, as they're lined up right there. So the first thing that we know right away, like right off the bat, is that these hydrogens, like nothing's happening with them. They are not reacting, they are not shifting, they are not changing whether they are up versus down, so they are going to stay intact in the product. I'm going to draw that in a different color, make it easier to see, like that. So the connection that we're forming between these two monosaccharides is going to be between these two functional groups right here. Now, if you're looking at videos or, if you're looking for a higher end description on how these two monosaccharides come together, if you're looking for like the nitty gritty details, there are rules about which one loses the hydrogen and which one does not, which one loses the OH and which one does not. But for us, for this class, for you guys, those rules really aren't that important. You just need to know that you're going to connect these two molecules at this particular spot, and you're going to be connecting them with an oxygen like that. And notice that this connection is angled up like this. And the reason that that connection is angled up like that is because this bond is beta. And so we're already forced, because we have, I'm looking for a different color, because we have a hydrogen down and we are not allowed to move that hydrogen at all. The other bond on this carbon atom has got to be aiming up. And the same thing for the molecule on the other side as well. So because this hydrogen is sticking up, this hydrogen is sticking up, and it has to stay sticking up, we are forced to draw this connection down. And notice that that creates like a staggered arrangement between the monosaccharides when they come together to make the disaccharide, and that's different from what we see up here for maltose. Those two monosaccharides were just straight up side by side. And this, it's got some dimension to it. So let's talk about the glycosidic bond. Remember, the glycosidic bond is this bond right here, the one that connects these two monosaccharides. This is a 1,4-beta glycosidic bond. On sapling, you're going to see that written in this format, beta 1-4 bond. What does the 1,4 mean? The 1,4, as you know, is referring to the two carbon atoms that are joined in the glycosidic bond. If we look at our two monosaccharides, remember that you always start numbering like this on the very right-hand side. You do not get to be creative in your numbering on this. This is always how we number monosaccharides. So we are making the connection between carbon number 4 of glucose and carbon number 1 of galactose. And just in case you're curious, when we put these numbers together in the description of the glycosidic bond, we always just go from small number to big number. It's not necessarily from left to right in terms of the structure, it's just little to big. So that's what the 1,4 means. We are forming a glycosidic bond between carbon number 1 and carbon number 4. And then what does the beta mean? So we talked about this already, and I'm going to give you a more sophisticated explanation of where the beta comes from in the names. It's a little bit fancier than the way that we described it in the previous example. Get you ready for the next disaccharide. So when we're trying to decide if a glycosidic bond is alpha or beta, we are going to ask ourselves, is carbon number 1 of the 1 to 4, is carbon number 1 anomeric? Is carbon number 4 anomeric? And again, this is referring specifically to this 1 and this 4, the numbers that are describing the bond. So is carbon number 1 anomeric? Is carbon number 4 anomeric? Maybe you forgot what anomeric meant. It's possible. The anomeric carbon is the one in the monosaccharide. It's the one that determines if the structure is if the structure is alpha or beta. So for galactose, this is the anomeric carbon. This is the one that determines that it's beta galactose. And for glucose, this is the anomeric carbon. It's the one that determines that it's alpha glucose. So we're asking ourselves, is carbon number 1 anomeric? That's this guy right here. Yes, it is. Is carbon number 4 anomeric? This guy right here, no, he's not anomeric. So we pay attention only to the carbon that is anomeric, and it retains whatever its designation originally was. So since carbon number 1 is anomeric, what is it? It's beta. We've already decided that. And that's where that notation comes from. That's why we call it the beta glycosidic bond. The molecule itself, the name of the disaccharide, lactose, that is designated by the anomeric carbon of lactose that still has an OH group. Right? So no OH group here. And that means no alpha or beta designation. But yes, we have an OH over here. So where is it? It's down, so it's alpha. So this is alpha lactose. If this OH group was sticking up, this would be beta lactose, but it would still have a beta 1,4 glycosidic bond. Last question on this one, identify the acetal carbon, the hemiacetal carbon, and the anomeric carbons. Okay, so we already found the anomeric carbons. We're doing this for the disaccharide. All right, so where are the anomeric carbons? So the anomeric carbons are the carbons that dictated the alpha or beta designation back when it was a monosaccharide. So here's an anomeric. The right-hand point carbons from when it was a monosaccharide. There's our anomeric carbons. And then what about acetal versus hemiacetal? So the connection that we formed between the two monosaccharides is an acetal connection. So that's an acetal carbon right there. There's a lot of words on this worksheet. And this guy over here is a hemiacetal. Now, if you're feeling pretty overwhelmed, don't worry, you've got one more example.